My name is Murugakummar Chandran. I'm from Electronic System course, and this is my FYP title, which is IoT-based Smart Underground Cable Fault Detector. So for the introduction, power supply cabling networks are continuously expanding, and their dependability is more crucial than ever. The use of underground high voltage cables is expanding because of their resistance to the effects of pollutants, severe weather, heavy rain, and storms. Even if the technology for making cables is continuously growing, there are still factors that could lead to cable failure during testing and operation. A cable with proper installation and maintenance can survive up to 30 years. However, cables are prone to damage from improper installation or poor jointing, and also subsequent third-party damage from civil works like curb edging and trenching. So these are the examples of what causes cable underground cable failure, which is aging and degradation, animal interference, and electrical overload and voltage surges. Okay, what is the problem statement? So the problem statement is locating faults in underground power cables can be challenging and time consuming. Earlier fault detection methods are manual, labor intensive, and time consuming. Manual methods may not provide accurate fault localization information, leading to delays in repairs and prolonged outages. There is a demand for an efficient and accurate fault detection system for underground power cables. IoT-based underground cable fault detectors can continuously monitor cable electrical characteristics. Real-time real-time data on faults can be transmitted wirelessly to a cloud-based monitoring station. IoT-based detectors enable quick fault detection and location, aiding maintenance crews and authorities. The goal is to design reliable, cost-effective, and easy-to-use IoT-based system. The system aims to accurately detect and locate faults, reducing downtime and improving grid reliability. So these are my objectives: to investigate the failure of underground cable characteristics, insulation resistance, capacitance and inductance, types and root causes that provides the important information of the fault nature and spot. To develop the Internet of Things based on underground cable fault detector system that can troubleshoot and locate fault underground cables. To validate the performance of proposed IoT-based underground cable fault detector prototype in terms of its accuracy in identifying and locating defects with an acceptable margin of error for fault location detection. Scope of study. So the objective is identify and locate faults in underground cable lines from the base station to the targeted site. Detection method: voltage divider set up over the cable to detect cable line issues. Fault detection process: when a cable line is identified, structured combination of resistors generate voltage. Notification system: the ESP32 microcontroller notifies the client when the voltage indicating a fault is detected. Proposed solution: IoT based technology using the ESP32 microcontroller and built-in Wi-Fi to identify faults in real time. Data storage: detected fault cable data is stored in a cloud-based database called Blink via the internet. Access and analysis: authorities can access the stored data for further analysis and action. For the Murray loop test method, the advantages is accurate for short distances. The Murray loop test was accurate for determining the distance to fault that were relatively close to the injection point, typically within a few hundred meters. So the weakness is limited to single faults. The Murray loop test was only effective for locating a single fault in the cable. It might not be useful for identifying multiple faults. Sectionizing method advantages is improved system reliability. By dividing the system into smaller sections, the sectionizing method could improve system reliability by reducing the likelihood of widespread outages due to faults. Weakness is might not be suitable for all systems. The sectionizing method might not be suitable for all the power distribution system, especially those with limited redundancy or high fault occurrence rate. So for thumping method, the advantages is could locate faults over long distances. A thumping method could be used to locate faults over long distances, making it suitable for in large power distribution system. Limited accuracy is for the weakness. The accuracy of the thumping method was limited by factors such as cable type, distance, and ambient noise levels. So for the next one, the time domain reflectometry method, the advantages is can detect various types of faults. So TDR is capable of identifying different types of faults, including open circuits, short circuits, and impedance mismatches. It provides valuable information about the nature and location of the fault within the cable. So the accuracy can be affected, which is for the weakness. Connector splices or the discontinuities in the cable can cause additional signal reflection. These reflections can affect the accuracy of the fault detection and localization. For the arc reflection method, the advantages is high accuracy. So ARM offers high accuracy in locating cable faults. It can precisely identify the distance to the fault, which helps in efficient fault repair and maintenance. So for the weakness is sensitivity to environmental factors. So the measurements can be affected by environmental factors such as temperature, humidity, and electromagnetic interference. So the methodology, so there is 3 input and 3 output, which is the power supply, Wi-Fi module, and fault switches. And the output would be in the LCD display, LED buzzer, and also the website. So the main hardware and software, which is the ESP32 board, the 16:2 LCD display, the Blink platform, relay board, LED, buzzer, push button, and that's about it. So how does the system work together? So the system consists of ESP32, LCD, buzzer, Wi-Fi module, relay, switch, and light emitting diode, which is the LED, and power supply. The ESP32 is the main component of the system. It carries out all the operations according to the user's requirement. A program is created and uploaded into the ESP32 controller. The system is activated by turning on the power supply when it's normal condition. There will be zero faults. There is no indication from the buzzer, LED, or LCD. Whenever fault is detected, there will be indications from the above mentioned components. The fault information in the terms of cable fault location will be displayed in the LCD and be stored in the Blink Cloud database via the Wi-Fi module. The first indication occurs when the voltage varies across the cable line is in the form of sound, light, and then will be displayed in the LCD with the customized graphical user interface in a website, which helps monitoring process in real time. So this is the circuit diagram. This is the Blink GUI, which is the graphical user interface. This is the complete system. So when there is a fault triggered, so let's say on the blue zone, it will display 1 kilometer triggered on the LCD display. And if a second kilometer is clicked, there will be 2 kilometer, and also for the 3 kilometers. So there is 3 rows and there is 3 different faults, which is at 1 km, 2 km, and 3 km. And there is also 3 zones, which is green zone, yellow zone, and blue zone. So the advantages. So the advantages over existing solution is comprehensive fault detection, real-time monitoring, cloud integration, scalability, and flexibility. So the special added features for the comprehensive fault detection is the system quickly finds cable fault using an ESP32 microcontroller connected with a voltage detection sensor, a buzzer, an LED, and LCD for display. So real-time monitoring is users can view real-time detected cable fault online via website or mobile app, making repair works faster by engineer or technician. So the cloud integration, all the detected data as stored can be accessed from the Blink Cloud database, making it easier for the engineer or technician to analyze and fix the cable anywhere and anytime. So the scalability and flexibility, the system can be easily adjusted and customized for different places, and it's making it useful everywhere. So inventiveness, this system is designed and developed through the integration of various components such as an ESP32 microcontroller, voltage reduction sensor, a Wi-Fi module, an LED and LCD, and relay, which switches making it inventive to detect cable faults. This system is smart and efficient because it displays right away the detected cable fault on a website or mobile app and saves all the information online in the Blink Cloud database. So this system basically detects voltage changes due to cable fault and warns users to trigger problem with sound and or light. Also quickly sends messages to the cable fault location. The system can be flexibly adjusted to fulfill different user and needs applied location. The system holds significant potential commercialization in both residential and industrial zones. In residential settings, it offers affordable, flexible, and user-friendly solutions, making it accessible for non-technical homeowners. In industrial environments, it can be used as a useful maintenance tool to detect cable fault quickly so that the production downtime can be reduced and operation efficiency can be maintained, hence a less financial loss. Additionally, its scalability and adaptability contributes to its viability to cater a growing demand for smart cable monitoring solution. So the conclusion, in sum, this IoT-based underground cable fault detector seamlessly integrates hardware, software, and wireless data transmission. The ESP32 microcontroller efficiently controls the voltage detection sensors to collect cable fault data in real time and send data to the Blink Cloud database via the internet for storage purposes. All the data in the Blink Cloud database can be retrieved and displayed on a website or mobile app anywhere and anytime. This integration makes the system becomes robust, reliable, and practical in detecting and locating cable faults. So future improvements, firstly expanding the fault distance range would allow for more precise fault localization. Secondly, implementing multiple fault detection channels would enhance the system's coverage. Additionally, an enhanced GUI and thorough testing and validation would further elevate the project's effectiveness and user experience. By incorporating these improvements, a more comprehensive and reliable cable fault detection system can be developed. Thank you.